Good afternoon and good morning, everybody, wherever you are. My name is Imran Hussain.
My name is Jamie Thomson.
And welcome to Google Cloud Data User Group for another smashing and very informative session on the usages of data on Google Cloud. And really focused again, contributing to a meetup group that's all about learning, sharing, and being inspired by the usages of data on Google Cloud. So today, actually, I'm presenting from a place called Peniche, which is a surfing hotspot of Portugal. The meetup goes on, so I've taken a break to do this. We're very fortunate to be joined by Jamie Thomson, who is a technical lead at Dunnhumby, a very prominent name in the world of customer insight and data science, especially the grocery and retail sector. I'm sure Jamie will talk more about that. As always, this session will be aiming to wrap the session up within the hour. We want to keep this as interactive and as conversational as possible. So we will be using Slido for polls and questions. So do feel free to ask questions as always at any point during the session, and we will we are setting aside some time at the end to hopefully go through and cover those off. We are also using Slido as always to get a feel of the audience, and we're going to start by asking some questions. So, where are we? Sorry, my bad. Here we go. So first question is, where are you joining us from? It's always great to get a feel of the variety of the diversity of our audience and the far-flung corners that we are joined from. So feel free to tap in your location at the moment. So we have London. Thank you, our hometown. Anywhere else? Don't feel shy. Okay, so we have a shy audience today, not a problem. Moving on then to the next question, relating to the main subject of the day, which is the session, which is Dataproc, Google's managed Hadoop service. It'd be great to know where you as an audience are in terms of your usage of Dataproc. 3 very simple options. Again, it's always good to understand where we are and in terms of the audience and the level of usage and familiarity of the subject. So, got an even split between the 2 submissions of someone who has not used it before but is clearly interested, 4 submissions in fact, and others who are playing with it. So, Jamie, we've got a audience there that is in its early stages, and I'm sure will really benefit from your experiences. So, without further ado, then I will introduce Jamie Thomson. Jamie, over to you.
Thank you, Imran, and thanks everybody for joining us today. So, as Imran said, my name is Jamie Thomson. I'm a software engineer at a company called Dunnhumby in the UK. We're a company of about 2,000 people globally, based primarily in Hammersmith in West London. So my talk today is called Democratising Dataproc. The code here, DA210, refers to this presentation that I gave actually over a year ago now at Google Next in San Francisco. And I'm actually reusing the slides from that session, hence why it says that on there. So just bear in mind that these slides are actually over a year old. I just want to make that disclaimer, and that I will point out some of the things in the slides which might have changed slightly in that time, but pretty much everything that we're talking about today is still relevant as it was back in spring 2019. So this session is called Democratising Dataproc, but it might easily also be called Our Journey with Google Cloud Platform. I'm going to touch on some of the decisions that we made during the course of our journey of moving a lot of our business into the cloud, and what we've done with Google Cloud Platform in that time. So a little bit of an introduction to what Dunnhumby do. So it says here, we empower businesses everywhere to better compete and thrive by putting their customers first. So our main thrust for what we do is helping our clients better understand their customers, and our latest tagline that we use is we are the world's first customer data science company. That's how we like to think of ourselves. So we specialize in a number of areas, including category management, so maximizing the investments that our clients make through data-driven category planning and execution, and we've got a number of products focused around that. We have Dunnhumby Media, which is all about reaching the customers of our clients at the right place at the right time with the right message, and we have offerings around price and promotions as well, helping our clients to price their products competitively and plan what promotions they should be carrying out upon them. And we do all this through a combination of data and science, and that's kind of our reason for being, if you like. So where do we do this? We have 78 retail clients. This is one of the slides which probably needs updating. I think we've got a lot more than that now. We've captured quite a few clients in the last year or so. So those are the retail clients are typically big brand retailers, supermarkets, generally grocery retailers, and we also have over 1,000 consumer packaged goods clients as well. In our data corpus, we have about 800 million customer records. So we track data on about 800 million customers globally, and our data scientists carry out analyses on a corpus of about 44 billion baskets every day. That's not to say we have 44 billion baskets worth of data arriving to us every day, but that's the corpus of data that we own and our data analysts use on a day-by-day basis. And on this slide as well, you can see the markets that we operate in and some of our clients in those various markets as well. So what do we do in a very simplified way of putting it? This is probably quite similar to a lot of companies out there. Typically, our clients will send their data to us, and when they do that, we will assign a team of data engineers to work on the data that our client sends to us and transform that data into what we call a common data model. So we try and make every client's data look the same so that we can carry out analyses upon it. So we have products that sit upon that common data model, that consume data from that data model, and we have products in the three areas that I talked about, which are category management, price and promotions, and media. We have legions of data scientists which run algorithms upon that data. A lot of the work that we do is offering bespoke consulting to a lot of our clients over and above the products that we offer, and we do that with our teams of data scientists that we have throughout the world. And typically we deliver our services and analyses back to our clients via APIs and data visualizations. So in a nutshell, this is what Dunnhumby do and how we make money. So we've existed for a long time. We've been doing big data since before the term actually began. We're primarily known for being the engine behind Tesco in the UK, behind their club card data program. So we'd run a lot of the data analysis for that, and we've been involved with Tesco since the early 90s. And in all our work in that time, we've been using what might now be considered a bit of an old tech stack. So we ran on Oracle Exadata. We used SAS for data processing, and we used a tool called Redwood Chronicle for scheduling and workflow management. These are all packaged products. They come with a big price tag, and they're all proprietary as well. So that's the tech stack that we used to run upon. Now, we made a bit of a decision about 3 or 4 years ago that we needed to change the way we were working. Our clients were coming to us and with different requirements, and we felt that we needed to make some changes in the way that we delivered services to them, in a way that made us more nimble and more able to react to what our clients actually needed. So we call that program of work Tech Renewal, and this was all about renewing the technology stack that we built upon. And we made a few big choices in that time. One of the main ones was that we made a big investment in adopting Python as our primary language for doing data science. So typically all our data scientists today will be writing Python code. We made a big bet on Apache Spark, which, for those that don't know, is an open source data processing engine, now maintained chiefly by a company called Databricks. It's a tool that works in the Hadoop ecosystem. And as I said before, it's a tool for doing processing of massive amounts of data. So we took a big bet on Spark and using that as our big data processing technology. We use Apache Airflow for workflow management and scheduling. We use Jupyter notebooks for visualization and for data exploration. This is typically the tool that our data scientist teams will be using. We also made a big bet on using an open source technology called Terraform. Terraform is a tool from a company called HashiCorp that enables you to manage your infrastructure as code. What that typically means is we can write Terraform scripts which actually which Terraform can understand, and we can use those to actually create the infrastructure that we need in GCP. And the great thing about those scripts is that we can commit them into source control and make changes and track all the changes just like we can normal code. So Terraform code enables us to manage our infrastructure as code, just the same as we do regular code. It's been a great asset for us. We use Grafana for visualization, for dashboard visualization. And the other big bet that we made was we made the decision to go with Google Cloud Platform as our chosen cloud provider. We are not platform agnostic, but for the things which I'm going to talk about in this session, Google Cloud Platform is a platform that we primarily use for offering these services. And the other big bet that we made was on a product in the Google Cloud Platform ecosystem called Dataproc, or Cloud Dataproc. This is basically Google's managed Hadoop offering. So if you've heard of Amazon EMR, I think they call it, that is Amazon's managed Hadoop offering. Dataproc is Google's competitor to that. I believe Azure also offer HD Insight. Dataproc is the one that Google use. And a lot of the talk today is going to be about Dataproc. So this program of work that I talked about, which is Tech Renewal, is providing Dunnhumby with quite a lot of benefits. So we're moving to a modern open source tech stack. We have a massive reduction in cost because we're not paying those big ticket prices for proprietary software anywhere. Moving to the cloud gives us many benefits. We can provision our infrastructure a lot quicker. We can scale it a lot more than we used to be able to. We can leverage all the investments that Google make in security and various hosting options around the world through all the data centers that they have scattered everywhere. And we're also finding it provides new opportunities to us as well. We're finding that other companies want to talk to us more when we can offer our products and our services in a cloud environment. So one of the cornerstones of what we do and what I'm going to talk about today is this thing that we call transient Dataproc clusters. Google actually referred to them as ephemeral Dataproc clusters. Why we used a different name, I don't know, but essentially they're the same thing. And what that pretty much means is if we're not using these clusters, we turn them off. And I'm going to talk a little bit about how we do that. So there is a blog post on Google's website that explains a lot of the theory behind this notion of ephemeral clusters. The link to the site is at the bottom of this slide. We'll make the slides available later. And essentially what this does is explain how to run these ephemeral clusters, which are clusters which get shut down when you're not using them. And I stole a diagram from that blog post, and I'm going to show it here. So if you're familiar with the Hadoop ecosystem, these things all mean something to you. So imagine a client which needs to connect to a Hive data store. So Hive is the technology within the Hadoop ecosystem, which makes files appear as databases and tables with columns that you can write SQL statements against. So Hive is one of the lingua francas for talking to data in a Hadoop ecosystem. And typically we have Hive clients that need to talk to that Hive data. What we're depicting here is two of these ephemeral Dataproc clusters. Each of them runs some of the key components of the Hadoop and Hive ecosystem. They run Hive server, they run a metastore service, they run a piece of software called Cloud SQL Proxy, which enables the Hive metastore to talk to a Cloud SQL instance running within GCP. And that is all part of a Cloud Dataproc instance. But the key thing to take away from this is that one thing that is shared by all these ephemeral clusters, or transient clusters as we call them, is the information about the data itself and the structure of that data. So the data itself is stored in GCP cloud storage, depicted here in the yellow box, and what we call the Hive metadata, the bit that describes how that data maps to tables and databases, etc., is all stored in a Cloud SQL instance called the Hive metastore, which is notionally referred to as the Hive metastore, which is a Cloud SQL instance running on GCP. So those two things, the data itself and the Hive metastore, which describes the structure of that data, is all stored in a central place, and it can be connected to via many ephemeral clusters. Hope that makes sense. That's kind of the cornerstone of what we do. So we offer these transient clusters to two different communities within Dunnhumby. You might remember on an earlier slide I talked about how we have teams of data engineers who are responsible for getting a client's data and transforming it into this common data model that can be used by our products and services. So our data engineering teams will use these transient clusters. They are short-lived in nature. We encourage our data engineers to create one of these clusters as and when they need it, run some work upon it, and then shut that down when they no longer need it. And the way we enable them to do that is we've provided some custom Airflow operators, so operators that work within Airflow itself, which actually know how to create one of these Dataproc clusters and shut them down in the manner that we want to run them. So we have custom logic within there that understands how we want to create our Dataproc clusters, and we can manage that through Airflow. We label each of these clusters per the function they're actually doing. So for example, we might label them as ETL to say they're carrying out some ETL operation, or it might be aggregation. We let our data engineers choose, but we do encourage them to label these clusters using GCP labels so that we can actually differentiate the cost of all these different functions that people are carrying out upon these different clusters. We can aggregate the information, aggregate the cost data, so that we can find out how much each of these functions is costing us. The other key thing about these Dataproc clusters, which enable them to be short-lived, is that we schedule them for deletion. And I'll show you a little bit about that on the very next slide. So when you create a Dataproc cluster, there is, you may be familiar with the command line that I'm using here, which is using Google's gcloud tool. When you actually create a Dataproc cluster, which you do by issuing gcloud Dataproc clusters create, there's an option to specify a max idle time, and that is the time that the cluster will live for without any activity before it automatically gets shut down. So Google will take care of shutting that cluster down for us when it's no longer being used. As I said before, we do enable our data engineers to shut clusters down when they're not using them. However, it's a fact of life that sometimes people forget to do that. So we have this max idle setting that actually shuts clusters down when we're not needing them as well. And typically we set that to 10 minutes. This is one of the slides which needs updating, actually. This max idle setting used to only be available under G-Cloud Beta. I believe that's no longer the case. It is actually no longer considered a beta feature. So I talked there about transient clusters for our data engineers. I'm now talking about the transient clusters that we offer for our data scientists. So we do offer the same short-lived clusters that I talked about before. That's where we encourage people to create what we call a job scope cluster, which is a cluster scoped to just doing a specific job. However, the very nature of what data scientists do is they need ad hoc infrastructure just to carry out, they need infrastructure to carry out ad hoc analyses whenever they want. We don't want our data scientists to have to wait to create a Dataproc cluster, which can typically be about 60 seconds wait. We want to give them the ability to run their analyses in an ad hoc fashion whenever they need it. So because of that, we also offer a Dataproc cluster, which is auto-scaled. This means simply that when more people are piling on that cluster and using it, that cluster will actually expand or contract depending on the number of people that are using. So we auto-scale that cluster by creating more nodes within that cluster as more people are using it. We wrote a tool internally to do that called Tidebell. We were considering open sourcing that. However, we decided there isn't a lot of point because Google now provide an autoscaler built into Dataproc anyway, and a lot of the work that was done on that autoscaler was based on a lot of the findings that we had from writing Tidebell. Okay. So just to drill down a little bit on these auto-scaling clusters that I talked about, we do still use our internally built tool, Tidebell. We do have a plan to migrate to Google's own auto-scale clusters. We haven't done that yet. So the way Tidebell works is it monitors cluster utilization via the cluster's Yarn API. We also use preemptible nodes. For those that don't know, preemptible nodes are an offering in Google Compute Engine. They are essentially nodes that Google will will shut down and take back from us with about 5-minute warning. And the reason they do that is to preserve capacity in their data centers. The advantage to us is that they're a lot cheaper than using non-preemptible nodes. And typically the workloads that we run upon on these Dataproc clusters are fairly resilient to nodes being preempted. So if a node is to disappear, as it were, we find our workloads can handle that quite well, and it does result in a huge cost saving for us. As I said, we do expect to replace Tidebell with Dataproc's built-in autoscaler sometime in the future. So what this diagram is a screenshot from one of our Grafana instances that monitors activity across our Dataproc estate, across the whole company. What you see here is it's a depiction of the number of nodes that we are using across our estate within our Dataproc clusters during a 24-hour period. So you will see that in the morning, around about 8 o'clock, that number starts to ramp up. That's when people typically start coming into work. We do have many people in India, so that's why it starts ramping up. Probably about 6 or 7 o'clock in the morning UK time. And you can see that our autoscaler takes care of creating those nodes as and when they're required. The red line, the red shaded area at the bottom depicts the preemption rate. So that is the number of nodes that are actually getting preempted on a daily basis. So it's quite interesting to compare the number of workers that we have at any one time. The maximum shown here is 105. So that is literally the number of Google Compute Engine instances that are running at any one time across our Dataproc clusters. So just to talk a little bit about what our data scientists typically do, they will carry out our ad hoc analysis model development using Jupyter notebooks, using those auto-scale clusters that we talked about before, and we encourage them to use sample data sets as well. The reason being is simply a cost-saving one. If they're working on sample data sets, then we don't need to create as much Dataproc resource for them, and that means we save money. On doing that, they develop jobs to run against full data sets, and then we encourage them to run those jobs on the short-lived clusters that we talked about before. So we have auto-scaled clusters for ad hoc analysis and building the jobs that they need to do. When it comes time to productionize those jobs, we encourage them to run those jobs on short-lived clusters. And what we're looking at here is one of our cost reports that depicts our spend upon Dataproc clusters. So just to take you through this a little bit. So each cluster that we create has a label on it indicating which of our clients that cluster has actually been created for. So we can slice and dice this data by the client that we're actually running the workload for. Project is the GCP project that we're running the cluster in. We split our cloud platform into what we call different components, and a component is essentially a grouping of different resources. And two of the main components that we create are something called analyst platform and data platform. Data platform is the part of our cloud platform that we offer to data engineers. Analyst platform is the part that we offer to our data scientists. And so again, we can aggregate, slice and dice the cost data over those two components. We can slice and dice this data by the number of nodes in each of those clusters. So when somebody creates a short-lived cluster, they actually specify how many nodes they require in that cluster. So we can compare the cost of different clusters depending on the number of nodes, and that gives our people the capability to test out the effect of adding new nodes. It may make the work quicker, but is there a cost benefit to doing that? That's what we like them to try and analyze. What we also do is allow them, I talked before about labeling for whatever function they happen to be using. We actually call that a purpose. So by putting these purpose labels on the cluster, again, we can aggregate the cost data across these different purposes to see what functions people are doing that actually cost us the most money. Now, this is the real meat of this slide, really, understanding that every single line item on this report actually pertains to a different Dataproc cluster. So what we're looking at here is the cost of every single cluster that we span up in, well, this seems to be around April 2019. So you can see that some of these clusters, the cost of some of these clusters is as low as 16 pence in some cases. This is a bit of an exaggerated example. Typically, our cluster will cost more than that because we're running bigger workloads upon it. But just to emphasize that by putting these labels upon the cluster, we can get this fine-grained analysis where we know literally how much every single cluster costs us, which is very useful for us to know. So, in a single day at Dunnhumby, we've done a bit of analysis. This is over a year old now, so these numbers will have changed. But we know that we run about 17,000 compute engine hours every day. So that is a node in compute engine running for an hour. We have about 3,000 Dataproc nodes actually get started every single day, started and shut down. Roughly 525 of those get preempted, and that costs us about $7,000, $8,000 every single day. And we have about 175 data scientists using the platform. Overall, we have 35 clients in GCP. That's actually changed a lot. That number is actually closer to 50 or 60 now, I think. And across all of our GCS buckets, we have about 300 terabytes of data. That's changed a lot now as well. I suspect that's more than twice as big as that now. I think we're approaching about a petabyte worth of data within GCP now. So this is really the money slide in more ways than one. So this depicts the actual spending, the actual cost of servicing one of our clients in GCP. If I show you this, for this particular client, we introduced the use of transient clusters around about August 2018, and you can see that it instantly had a massive effect on our cost base. Introducing the use of these transient clusters, so the short-lived clusters and the auto-scaled clusters, has had a massively positive effect on our bottom line. Massively reduced the cost of providing our services to our clients. A lot of people do ask us, given the nature of what we're doing, which is a lot of data processing, and we're doing it in GCP, why don't we just use BigQuery? Well, the reason is basically that even though GCP is our preferred cloud provider, it's not our only cloud provider. We do expect to, we do want to give ourselves the capability to take what we do and host it on other clouds should we need to. Also, GCP isn't available everywhere. So, for example, in China and Russia, so we need to have it, the capability to to offer our services in those countries should we need to. For these reasons, we don't want to make a bet on technologies which only exist in one provider, which is what BigQuery is. So even though BigQuery is quite appealing, given its capabilities, we decided to not use it because we do strive to be cloud portable. Although there are a few, we do have a few in-house offerings for which we do actually use BigQuery. But for the products and services that we mainly offer to our clients, we chose not to do it. So a little bit about our solution architecture, how we put all this stuff together. So for every single client, we deploy a number of components within GCP. We have a virtual private network and cloud DNS around that. On top of that network, we deploy external proxies to limit what can come in and what can go out. We have an SSH gateway that allows us to SSH onto the machines running in those projects. And we also have a custom-built SSO proxy as well. What this enables is for our data scientists and our data engineers to access the various user interfaces that are offered on our platform, such as the Airflow user interface, Yarn user interfaces on our Hadoop, on our Dataproc clusters. So we offer a single sign-on proxy that enables them to log on with their work credentials to access those resources. We run the Hive metastore for anyone that's familiar with Hadoop and Hive. The Hive metastore is where we store the information about the structure of the databases and the tables within in which we store our data. So that Hive metastore runs upon a Cloud SQL instance, which is MySQL. And then we have our data platform. I talked about how the data platform is the part of our platform that we offer to our data engineers. So that incorporates Dataproc, Airflow. We do offer Jupyter notebooks to our data engineers also, and all of that runs upon cloud storage. All of our data is stored in GCS buckets. We also offer our analyst platform, and typically the audience for that is our data scientists. And again, in there we offer Cloud Dataproc. We offer the auto-scaled clusters that I talked about, and the short-lived job clusters. We run Jupyter, we run that upon Kubernetes, and again we use cloud storage as the means for storing data within our analyst platform. And we also offer various products on top of those as well. For every single client, we separate the resources that we create in GCP into what we call runtime and state, and we have a very clear separation between those two. So state is literally the storage of data. Runtime is the runtime components that we use to process that data. We separate them literally in terms of the state components live in a dedicated project, and the runtime components live in a different project. So it's really easy for us to differentiate the costs between those two things, and also segregate IAM permissions and things like that. There are a lot of benefits to actually separating these two things out logically across two different projects. So we have what we call a single-tenant deployment model, which means the solution architecture, which I depicted a couple of slides back, we take that and we essentially stamp that for every single client that we have. So we actually have many instances of this architecture. We deploy this architecture for every single client, and the reason for that is we want to offer security to our clients. We want to promise them that their data will never get stored alongside the data of another of our clients. We have that physical separation there by storing them in different dedicated projects. So some of the benefits that I just mentioned, we can segregate our access and our operations internally. It makes client access a lot simpler. We can give clients access to their data and no one else's data, but by controlling access to a GCP project. It makes it a lot simpler to operate for us. We have no need to use some of Hadoop's built-in identity access features, such as Kerberos. That's not something we need to worry about. Cost transparency is a massive benefit for us. Being able to just aggregate the cost per project allows us to easily see exactly how much it costs to service each one of our clients. And the other big benefit of this is for every single client, we can now scale from zero. This never used to be true in our old tech stack, where we had to provision infrastructure in our own data centers, sometimes years in advance of us actually using it. Now we have the capability, when we sign a new client, to take them to GCP and literally start from zero and build up as and when we need it. That's a massive benefit to us, and results in great cost savings as well. Okay, coming to the end of it now. One thing I talked earlier about how we use Terraform to create all of our infrastructure. So what I've done is made available a project on GitHub, which actually demonstrates how to do some of the things I've talked about using Terraform. So it's called Democratising Dataproc. The URL is at the bottom of the slide there. And to use this project, it's actually quite simple. This is taken from the README of the project. So all we have to do is initialize our G-Cloud tool. After actually creating a project in which we want to do this, we have to enable a bunch of services, specifically the Dataproc Google APIs and the Cloud SQL Google APIs. We specify which project we're going to use. We create a bucket, and then we can run a make command, which will actually go and deploy this infrastructure for us using Terraform. And we can tear it all down again by using make destroy. So if you wanted to, you could go and clone that project right now, run these commands, and if everything works okay, which I think it should, you could have yourself an infrastructure running multiple Dataproc clusters, all sharing the same Hive metastore instance within 10 minutes, should you so wish to. So what is being depicted here is all the different resources that actually get created if you were to run those commands. These are the things which actually get created in GCP. So the yellow boxes all pertain to a network which actually get created. We have, in red, we have things which are used by the Cloud SQL instance, which hosts the Hive metastore. In purple, we have a bucket which actually stores the actual data. And in blue, you will see that we have those two it creates two Dataproc clusters for us, each of which is pointing to that single Hive metastore instance and that single same storage bucket, which is where the data gets stored. So it really emphasizes that we have two clusters, both sharing the same data and the same metastore. And the green boxes are some jobs which get run upon them as well. So if you were to go and run the commands that I showed you on the previous slide, this is literally what would go and get created for you, and some jobs would get run. So some lessons learned from all this. When I actually did the talk, I went around to some of my team and asked them to just list a grab bag of things that I might be able to share with people who are at the talk. So I'm just going to run through these very quickly. So upgrades are difficult because of the shared Hive metastore. We do have problems created by the fact that we have different communities using that shared Hive metastore. We have to schedule downtime at the moment to make sure that basically we don't break anything for anyone. We found out recently, in fact, Google have announced very recently, they've got a new service coming where they will actually host the Hive metastore for us, and we're hoping that to make use of that in the near future, just to alleviate some of the headaches that we have around this. We recommend you peg Dataproc to a minor release rather than a major release. We have seen instances where a change to a minor release can actually break functionality. Google claim that should never happen, but we have seen it happen. So just thought I'll mention it here. Stack driver logs. These are the logs which is where the output from Dataproc will end up. They can grow very quickly, so we recommend you use log exclusions and less chatty log4j config just to reduce the amount of logs that you're storing. Otherwise, they will become quite expensive quite quickly. I said we use Terraform, and we do. It's worth knowing that sometimes the provider does lag behind what the Google SDK actually offers. We have had to make upstream commits ourselves to that Terraform provider just to leverage some of the new offerings in the Cloud SDK for some things that we actually needed. In shared clusters, users can easily crash the master nodes where driver runs on the master. So change the default deploy mode to cluster. That's an easy thing to do. If you're familiar with Dataproc, you have a number of deployment modes, one of which is cluster, and that's one we recommend that you use. Yarn application masters can fail if scheduled on preempted nodes, and node labeling can prevent this. Yes, we should never run the master of a Spark job on a preemptible node, because that node might disappear while the job is running. The default Spark config in Dataproc can cause an individual to max out the cluster. So yeah, just be careful how you configure Dataproc to make sure that actually can't happen. Users need the Spark and Yarn UIs, but it's really hard to make them secure and available via the authorization proxy that I talked about earlier. It is a difficult thing to achieve, but your end users won't thank you if they don't have access to the Spark and the Yarn UIs. Conda is useful for building consistent Python environments across Dataproc and Jupyter notebooks. And we use Google Cloud Storage retention policies on temporary data sets to make sure that they aren't hanging around too long and costing us money. Okay, that is pretty much everything that I wanted to cover. I got it in sufficient time, I think. I hope that was useful. A little bit of a journey through what we're doing with GCP and specifically with Cloud Dataproc. So thanks for coming along, and like I say, I hope it was useful.
Thank you, Jamie. Thank you for a really informative talk. Clearly, very expansive usage of Dataproc across Dunnhumby and the use cases that you talked us through. What we'll do now, Jamie, is look at the questions that have come through and get your view on those. So taking them from the top, when would I want to use Dataproc instead of Dataflow? And I guess this is your opinion as much as anything else.
Yeah, well, actually, in this day and age, perhaps Dataflow is the thing that people want to use. We are looking at ways that we can move to that in the future. Typically, right now, a lot of our retail clients still work in a batch mode. They still deliver files to us via SFTP. Quite literally, that's how we receive a lot of the data. So a lot of our clients are not set up for streaming data to us right now. That said, we are looking at Dataflow as an option, and it's something, yeah, we are currently evaluating. So
okay, different
strokes for different folks.
Absolutely. And are there any use cases, of course, or considerations to use Spark in a streaming mode from within Dataproc?
It's not something we're actively looking at, but all options are on the table at the moment.
Sure. Second question, so it's really coming back, clearly it struck a chord, the usage of the reasons why you would use Dataproc versus BigQuery and Bigtable. I thought the answer that you gave was fairly clear. I don't know if you want to contribute to that or
yeah, no, I can reiterate. Maybe the question was asked before I referred to that. Yeah, basically we want to make sure that we're cloud portable. So we want to use technologies that we can use on different clouds, and BigQuery isn't one of them, basically.
Okay, and why Grafana over Google Cloud Stack Driver?
A good question. I'm not really sure about that one. Offering Grafana enables us to tailor the experience a little bit better, and it's a technology that a lot of people were familiar with already because we were already running Grafana on our on-premises infrastructure. So in order to maintain consistency between those two things, we chose to use Grafana. But that said, we do offer our data engineers access to Stack Driver as well. So they do have the option to use Stack Driver should they need to.
Right, and it's interesting that there seems to be kind of flavour of independence that's coming through in terms of the architectural choices that Dunnhumby have made, as you say, not betting all in, going all in on in terms of native services.
Yeah, exactly. And the other big bet that we're making is on Kubernetes as well. I'm running a lot of our products and services. And the reason is simply we want to remain as portable as possible. It's not, I'm of the opinion it's not really possible to remain totally cloud agnostic. We still have to do a lot of things which are specific to GCP. But if we can kind of standardize on some open source technologies, which are non-proprietary and work across clouds, and that does have some advantages to us.
Absolutely, great. So, Jamie, thank you for a really compelling session. You'd be glad to know that Leeds are still holding out 1-0 against Barnsley.
I'm very glad, thank you.
You haven't missed anything there.
I'll be turning it back on straight away just to get the final score. I might catch the last 5 minutes.
Absolutely. I'm sure, yep, you never know what could happen in the closing minutes. So without further ado, thank you, Jamie. Thank you, everybody.
You're welcome. Thank you for having me, Imran.
Not at all. Pleasure. And until next time, stay safe and have a great summer.
Cheers.
Thank you. Bye-bye.